Good afternoon, ladies and gentlemen. I am Anand Buddhadev, a member of the DNS-OARC Program Committee, and I will be chairing this session. Before we get started, I would like to express our thanks to two members of our community who have been working tirelessly and volunteering. I would like to thank Mauricio Vergara, who has been doing the webcast and the streaming, and Sebastian Castro, who has been doing social media for us. Thank you, guys. And with that, I would like to start this session. First up, I would like you all to put on your fireproof suits as I welcome Jan Včelák to talk about Flamethrower.
Thank you, Anand, for warm welcome. So yes, I'm Jan Včelák. I'm a lead software engineer at NS1, and Flamethrower is a DNS performance testing tool that we open sourced recently, and I would like to introduce it to you. So essentially, it's DNS performance and feature testing tool. It has been built as an alternative to DNSPerf. But no software is ever written without any motivation. So we actually had some good reasons to that. And because we are an operator that does these smart DNS tricks, traffic routing or non-standard DNS features, we have a custom DNS server, and about 2 years ago, we started a complete rewrite of it. And we needed some tools that would go well with it, like testing tools. So we have some good confirmation that we are implementing the code correctly. So the existing tools didn't work for us very well. We needed good source port distribution, for instance, because the way how we run our software. It was 2 years ago, and we were already thinking about DNS over TLS, which might eventually happen even between resolvers and authoritative servers. So as a prerequisite, we needed a good support for TCP. So that was one of the design goals. So we need a tool which would allow us testing DNS over TCP. We also wanted some tool that is able to generate realistic query patterns, and we needed something that would fit well into our continuous integration process or continuous development pipeline. I will get to these things a little later. But it was 2 years ago. Finally, in January or early this year, we managed to clean up and re-review the code, and we wanted to make it available for the community. So it's under Apache public license, so very permissive. And when we are looking where to place it, we asked DNS-OARC whether they would be willing to accept this under the DNS-OARC GitHub namespace, because we wanted this to be available to everyone, to researchers, to operators, to software developers, and we really want this to be a community project. So huge thanks. We are very grateful to DNS-OARC that they accepted this project. And so now it has lives in the same space where other fine DNS tools, DNS testing tools can be found, including, for instance, DNSPerf, which moved to DNS-OARC about 2 weeks after Flamethrower was open sourced. So I will talk about some internal architecture, some use cases, how we use it. At the end, I will mention some features that we implemented recently or were contributed recently, and some features we consider to be on the roadmap. But before I jump into that, I would like quickly show you how this tool works, so you got some sense, and my next explanations are not too abstract. So Flamethrower is a command line utility. It's the utility is called Flame, and you supply some set of named parameters or flags, and the name of the server that you want to test or exercise or flame. So in this case, on the left side, you see a really simple invocation of the utility. There are the first two parameters, the -r and -t, define that we will be sending SOA query for foo.example.test over and over. The -q specifies the QPS we want, the output QPS, so 2000 QPS, and -l just limits how long the flame should run, so this is only 5 seconds. And we will be flaming the server with the name ans-example.test. And when you execute this command, Flame will actually print a few lines, like describing what's going to happen. And then every second it will print out some basic statistics. So this output on the right side is actually trimmed where the lines are. So these printouts, like single line printouts, every second will just show you how many queries were sent so far, how many are in flight, how many have timeout so far. And at the end, you will get this like human-readable summary of the run, including, for instance, histogram of the responses. So that's roughly how you use it. And internally, the tool is written in so-called modern C++. It uses fine DNS library LDNS by NLNetLab, which we use essentially only to construct the DNS content that we are about to send. And it uses libuv, which is asynchronous library, C asynchronous library, to perform networking operations. So we don't rely on LDNS with this. And because libuv is a C library that uses callbacks, we actually found this really nice library, which is called UVW. It's just a simple header-only C++ wrapper for libuv that makes use of libuv in C++ much easier, or modern C++. So, for instance, in the code, you will never find any explicit allocation and the allocation of memory. Everything is handled with smart pointers or C++ smart pointers. So it's difficult to make a mistake in there. And also libuv is sometimes tricky to use because you have to set up various callbacks when some event is completed, and it makes the code slightly difficult to read. So because C++ provides lambda functions that can capture local variables, it actually makes the use of libuv slightly easier. So that's the internals. And as for the architecture, the tool essentially executes in this pipeline. There are some components responsible for various things. I'll just quickly describe what these things are responsible for, and then I will dive into some details on each of these components. So the first component is payload generator. So the payload generator is something that actually constructs the DNS messages that you want to send based on the parameters provided on command line. So this is pretty straightforward. The next one is traffic generator, which is a component that is responsible for either creating the sockets or UDP sockets and sending the generated payloads, or to set up TCP sessions or TLS sessions and keeping the sessions alive. And the traffic generator also is parameterized, and it essentially sends the messages in bursts based on the configuration. And if you want some more granular QPS control, you can do that in the next block, which allows to cap the output, the query rate of the traffic generator. And the last component is metrics, because we are interested in collecting the results in an automated way, readable to the user, but also in machine-readable format. So there's a couple of payload generators in Flamethrower. The simplest one that you have seen in the example at the beginning, that's just a single, we call it static. It just sends the same query over and over, and you can parameterize by the name and type only. So simplest one. The next one, the file actually reads a list of these queries from a file, and it's a DNS-perf compatible file, so it's essentially a text file that has a query name and query type on separated lines. Super simple. And then there's a group of payload generators that include some randomness. So random packet is one of these generators, and this actually doesn't generate valid DNS queries. It generates just random binary garbage and sends it to the server. And we actually found this really useful, not just during development of the server, but for instance, when validating our own network monitoring tools. Because a lot of the tools just capture the traffic and decode the messages and then just output what they have seen. But if you send a random garbage to the server, these collection methods usually don't output anything, or it's invisible for them. So we found this really useful. Similar to that is random QName. I'm actually skipping one. So random QName generates valid DNS queries, but puts random binary garbage into the domain names. So it adds prefix to the you define the record name and record type, and this generator just prepends some labels that contain random characters. And the DNS specification allows only a subset of printable characters to be used in domain names, but the wire format actually allows you to put anything there, including binary 0, for instance, like 0 bytes. So this is what this module does, and it also has proven very useful when testing our DDoS mitigation tools and monitoring. The number QName is very similar, except that the prefix is not, it contains just decimal number as a label. And random label uses the allowed characters that are normally allowed in domain names. And the random label is actually what, for instance, the Mirai botnet attacks used. So if you want to test your server or your defensive capabilities for this, you can use this model as well. And you can also configure, for instance, how many random labels should be added. So these are the generators. Then there is the next component, which is traffic generators. So once we have generated the payloads we want to send, we have to actually send them. So is this component. It's worth to say that Flamethrower runs only in a single thread. And we have seen that the max query rate on single core is about 100,000 queries per second. That's like the maximum we have seen on some normal machine. Of course, it depends whether you run it on high-end server or laptop. And if you want to use more performance of your system, you probably have to start, or if you want to use more cores on your machine, you probably have to start multiple instances. So the traffic generator takes the payloads and sends them out in batches. So there are 3 parameters on the command line that specify how many queries are sent. So you can, first of all, you can specify the number of concurrent traffic generators. So this differs for the use protocol. If you use UDP, it's essentially the number of sockets that are created. So if you set it to 100, you will see queries coming from 100 source ports. If it's TCP, it means that for each traffic generator, a new session is established. And Flamethrower tries the best to keep it alive. So if the server terminates that session, Flamethrower will reopen it immediately. So it will try to keep that many number of generators to be available all the time. So for TCP, it means you can have, for instance, 100 connections from the client, from Flamethrower to the server. And for DNS over TLS, it's essentially the same as for TCP. So once we have these channels where we can send data, so either UDP socket or TCP session, we send a batch of the queries. So there's a parameter -q, which like lowercase q, which defines how many queries to send at once. And then there is -d, which is a delay between the batches. So these two parameters actually, all these three parameters define the QPS of this traffic generator. But if you need some more granular control of the QPS, you can use these additional parameters that enable rate limiting for of the output packets, essentially. The algorithm it uses, it's just a simple token bucket algorithm. And there are two options. There's either like static QPS for the whole run of Flame, that's the capital Q parameter, or you can actually specify a QPS flow. So the QPS flow, it's a list of pairs where there's always the desired QPS and the length of that time period in milliseconds. So in this example, like I run 1,000 queries per second for 60 seconds, 100 queries per second for 60 seconds, and so on and so on. And on the bottom, you can see some output from Grafana that just captures such run. Actually, it should look like a square signal, but because I was collecting the metrics with 30-second sampling rate, it looks more like a SAW signal. But this is useful as well because, for instance, this QPS flow can be used to simulate a cold start of a cache of a resolver with a cold cache. But also, like the square signal, we have used it very useful when we are rolling out our new DNS server, and we wanted to make sure that the whole query or metric processing pipeline works. So we just generated a signal at the DNS server by flaming the server, and we checked our dashboards whether we see the signal or not. And the last component is metrics. So you have seen that sample output in the first slide. Here's actually untrimmed version of it. So Flame can generate something that is readable to users, to humans, and also something that's readable to the machine. And so if you run Flame with this -o parameter, it will actually switch the output format to JSON, and every second it will dump this huge blob of JSON, which contains essentially everything that you see on the left side. But you have this with a granularity of 1 second. And the motivation for this was that when we were developing the servers, we essentially we had some goals for the performance. So we started by writing a simple DNS echo server, and then we started implementing the features. And we want to make sure that we are not degrading the performance too much, or that as we add features, the performance degrades in some expected way. So that's why we implement this output format, and it's actually part of our build process. So when we or integration process. So when we build a new version of our DNS server, it automatically runs Flame with some predefined parameters and dumps this JSON into Elasticsearch. And in Elasticsearch, then you can, or you can use Kibana to visualize the data so we can see some trend. Unfortunately, I haven't found some recent data that would be nice to show. So you will have, the JSON will have to do. I have a couple of examples how Flame can be invoked. So the first example is pretty simple. It's essentially reads input from DNS-perf compatible file, sends the queries out at the 2,000 queries per second rate, and so that's pretty straightforward. In a second example, I want to show something more complicated. So this is actually random label, so the Mirai botnet-like queries, which will have a single label prepended to the domain example.test, and the label will be up to 10 characters. And it outputs into JSON, and actually, instead of targeting a single server, it targets multiple servers. That's a feature we added really recently. So instead of specifying the names of the servers on the command line, you can actually add --targets and read a list of the servers or IP addresses from a file. And the Flame then like round robins the queries, or not the queries. It round robins the allocation of the sockets or the TCP connections. And in the last example, I just show how you can send some random garbage on TCP IPv6 to the server. Simple as that. And as for some other features, we recently finished DNS over TLS support was added like 2 weeks after we open sourced the server. This feature was actually contributed by Jim Hague from Synodum, who is not here, but sometimes comes to DNS-OARC. So huge thanks. It was a great surprise for us because this was on the top of our list of stuff we want to implement. And we got it in 2 weeks after we showed up the code to everyone, which is great. And like a couple of weeks ago, we added the feature to target multiple servers, which is helpful. In our case, it's helpful when we are doing some DDoS security drills, because we use Flame for that as well. And at the last IETF, during the hackathon, me and Shannon Wayrick worked on like a little fun project. We tried DNS over Quick support, and we needed some client code for this. So we have a PR in progress. Shannon is still working on that during his morning commutes in train. So in case DNS over Quick happens at some point, we will have tool to test it. But there's still some things we would like to add. We definitely want to improve the execution on a machine with multiple processors. That's one thing. The query rate patterns, like the QPS flow is relatively flexible, but we would like to use something even more realistic. So we are thinking about extracting these query rates from PCAP. The performance is fine. It's fine for our use case. We actually focus more on the features rather than the performance, because there are some other tools that focus on performance primarily. But we might want to improve that. We are thinking about source address spoofing and, of course, DNS over HTTP support, but that's really low on the list. And I think that's it. If you have some questions, I will be happy to answer. If you try Flamethrower, we'll be happy. We are interested in your feedback, essentially. And there's also, I think, Docker containers. So if you don't want to build it, you can just download the Docker container. And thank you.
This is Andre at ISC. I just wanted to say thank you, because we missed the TCP testing tool, and we already used Flamethrower to crash bind. So thank you.
You're very welcome.
Hi, Dwayne Wessels from VeriSign. So also, thank you very much. I think this is very cool. And I realize since it's open source, this may be silly, but I wonder, does the tool have anything to prevent it from very easily being abused? You know, is there some sort of feedback like, hey, I'm actually getting responses and I should stop if I'm not, or something like that?
No, there's nothing like that. We have thought about it, but because this tool doesn't support IP address spoofing, it's on the server side, it's relatively easy to mitigate like eventual unappropriate use of this tool, because my impression is that if there's some script kiddie, they cannot just use it from scratch. They would have to be more smart about how to use it in a bad way.
Okay.
Ralf Weber, Akamai, also to kind of also say what Andre said. I mean, big thank you. We are also using it to test our DOT implementation.
Cool.
And one thing about DNS over Quick, I mean, you said you had problems with the client code. What did you actually run against it as a server, or what was the plan?
So yeah, this was kind of coincidence, because before IETF there was NetDev conference and there was a workshop on Quick protocol. So we kind of find it well suited for DNS, and we wanted to try. So on the server side, we actually wrote a simple proxy from Quick to UDP in Go, which was only a few lines of code, is actually on our GitHub as well. And for the client side, we wanted to use Flamethrower.
So you also don't know of a good library that you could use for DNS-OARC quick for C?
Yeah, I don't know. What we used a library called Quickly, which is implementation from Fastly. It's still in progress. The protocol is in progress. But it worked reasonably well. And for the Go part, for the server part, we use quick-go or go-quick, one of these.
Thanks.
You're welcome. So thank you again.
Thank you very much, Jan. Up next, we have Ray Bellis from ISC to talk about serving the root zone from within an authoritative, a caching resolver.
Or not, as the case may be. Right. Hopefully I'm a little bit recovered from this morning. Okay, so as often happens in research, where I ended up isn't quite where I intended to end up when I started this particular project. So hopefully most of you are here familiar with RSC 7706, talking about local zone mirroring of the root zone. My general view is that actually 776 is currently written as too proscriptive. Sorry, excuse the typo on the slides. It's very rigs about saying you're going to be doing stuff on the loopback interfaces, and it's not actually a deployment model I particularly agree with. I don't think you actually need to put the root zone into every single system, because that's going to result in every server having to get XFR support. Arguably, you could have a local XFR master that's going to get the root zone from one central place and then distribute that. But if you're going to set up that infrastructure, why not just actually send out, have that system respond to root zone queries directly instead of the zone as a whole? A single local instance of the root zone, and I'm clear here that it's not a full root server in the Anycast sense, but just a server that contains the root zone, could actually handle almost unlimited number of local resolvers. So what I've ended up with, but as I said, this wasn't actually really where I was intending to start, is a proof of concept server that just does the root zone. I have actually, in fact, reinvented NSD1, but that wasn't the intention. The intention was to actually learn more about Linux networking. So this is a server where it loads the root zone from a normal XFR format, or master zone file format zone file. It then pre-compiles every possible answer, positive and negative, that might be required. Obviously not the answer section, sorry, not the question part of the answer, but everything following, so the additional authority sections and so on. It does support compression, so all of those answers are pre-compressed. More on that in a moment. For performance, it uses raw sockets, and on a moderately sized box, it's quite happy to saturate a 10 gig network pipe. Saying about the zones, it is very much root zone only at this point. You couldn't deploy this currently as an Anycast root server instance, because all of the root servers also serve the .ARPA zone and the root servers.org zones, and this server does not do that. So if you were to try to run up this server and borrow one of the real root server's addresses and pretend this was a real root server, it wouldn't work. Please do not do that. Not only would it not work, but yeah, it would probably kind of annoy the other root server operators. So currently the method I use on my own home network to deploy this is use static subzone support in bind. So I basically say if the query is for the root zone, but specifically only for the root zone and not for the children of the root zone, send the queries to this box instead. And the static stub's needed for that, because if you just try to use the alternative subzone support, it would also send the child queries of everything below the root to the server instead, which would then clearly fail. So go back to pre-compiled answers. Load up the zone and parse it. Ironically, I'm using the LDNS library also for doing this. It's actually quite nice and lightweight for doing this. On the compression, Obviously, it will have occurred to people, hopefully already, that if you don't know how long the question is going to be, then you don't know exactly where the compression pointers are going to point, because compression pointers are relative to the start of the packet, and you have a variable length section, that is the query section, before you actually get to where the answers are. So what I do is, say for example, if it's a query for something.uk, when I'm building the answer for UK dot, I assume that the smallest possible minimized query, in this case it'd be 4, so you'd have 0 to prefix length, UK 00 for the root label. So I assume that that's the absolute minimum length of the query that's going to be coming in, and that's the default compression offset. And then if a longer query comes in, the resulting packet is modified on the fly, because I retain a table of exactly where the compression pointers are, to say, well, I've got to add so many bytes onto the compression pointers, so they're basically adjusted on the fly very quickly. But if the query came in pre-minimized, this has the advantage I don't need to modify the packets at all, and it's basically blat out the packet as fast as I possibly can without making any changes to that packet. For performance, I am using raw sockets. I have looked at things like netmap and dptk. I took the raw sockets approach because at this point I wanted to be able to run on systems where I didn't want to dedicate a NIC to packet answering. I wanted to be able to run even on single NIC systems. But as I know Jeff Houston's found previously, and when he did some work on raw sockets, if you try to use raw sockets with the IP address that the system is itself configured for, the kernel will get in the way. If you try to send a connection to port TCP53 on the system's IP address, but the server itself is not listing on TCP53, the kernel will send you back a reset and promptly kill your connections for you. So what I'm doing instead is basically having the system configured with an IP that doesn't exist on the local area network, statically configured, and the operating system has no idea whatsoever that that IP address exists on the system. So the operating system kernel will not respond to ARP requests for it, or in any way basically say, I don't know what to do with that packet. But in order to therefore make the system available to the rest of the network, that means I have to actually handle things like ARP requests. So if the rest of the network says, where is this IP address on my network, my little server will actually fire up and say, I'm here. And it does that not just for IPv4, but it also implements IPv6 ICMP network discovery, ICMPv6. So as soon as the server starts, that IP address is both for IPv4 and IPv6 appears on the local network. That said, it does not support any form of forwarding or routing. So you can only talk to this system from the local area network. And I'll maybe come back to Dwayne's question from the last talk about how you make sure that can't be used for DOS later. So again, talking about raw sockets and TCP, actually, I didn't really want to do a full TCP stack on this one. Most of the time it's not needed. So I did implement the stateless TCP that Jeff Houston and George Michelson worked on some years ago, where basically when you get a packet coming with the appropriate TCP headers, you send back all of the 3 or 4 packets that might normally result in that TCP stream, but you don't actually care what the client does. If the client happens to drop a packet and say, I didn't get that, you say, fine, try the whole stream again. So you can't use that for persistent TCP streams. It is basically fire and forget. So SYN comes in, and I basically send them straight away back, SYN-ACK, and then a datagram, a data PDU, another data PDU, the final one back with a FIN. And as far as the server's concerned, that's done then, it's stateless. And it doesn't remember anything, so it has no memory overhead. Because it's not persistent, you wouldn't want to try and use this for XFR. I do not want to try and send back 2,000 packets in response to one single inbound request for a TCP XFR. But if you're using this on a local area network, which I said, which is well the same for anyway, because there's no routing support, it's more than good enough, and it's very fast. Still doesn't necessarily mean it's a good idea. Looking at Jeff over there, laughing away to himself. But it does work, and it's not that hard to implement. Let me just, oops, okay. the entire code base for this, and bearing in mind that I've got both a DNS server, I've got an IPv4 stack, an IPv6 stack, stateless TCP, ARP, ICMP ND, all the ICMP, the whole thing is 3,500 lines of C++ code. So I think I said on one of the earlier slides, on modest hardware, this thing's doing 10 gigabits per second. It will also run on a Raspberry Pi. That's right, well, that Raspberry Pi, there we go. 15,000 queries per second on a Raspberry Pi 3B. It'll probably do 17,000 or so. That is not a huge number by today's standards, but for a Pi, it's pretty damn good, I think. I haven't checked the latest bind code, but a slightly older version of bind before we refactored the network stack would peak out at about 3,000 queries per second. The memory footprint is tiny. I've used a, ironically, very, very heavy SDK, the NARD SDK, and I'll come back to heavy in a moment, to build a distribution for the Raspberry Pi on which you can basically plug this in. You just load an SD card up, copy over the image, use a text editor to edit a single text file that's in the boot partition, turn it on, and you've got a root server. And the whole distro is 43 megabytes. So it's not like, loads of you do things like ADSB receivers with Raspberry Pis and their SD card images. It's not a 1.5 gigabyte Linux distro. It's a very, very lean and mean, basically build system, resulting build of only 43 megabytes. That's all you need on the card. The NARD SDK itself is pretty heavyweight because it includes the entire tools cross-chain that you need for compiling the kernel and the compilers and everything else that goes with it. So you actually need about 20 gigabytes of disk space and a few hours to spare just to build the thing. And that was a bit of a surprise just how much that took, but it works, and you get this lovely small distro coming out at the end of it. And here's about where you can find the stuff. So the server itself, of course, are called fast root, so we call ourselves fruit, and that's where you can get the fruit source, and there's where you get the fruit pie. Excuse the puns. So I first started this project because I wanted to find out about Linux network performance, and so I'm going to talk a little bit about this. Sorry, 1 second. So if you've used any modern, reasonably high-end system, I haven't actually checked what the Pi does, you'll find that the network interface cards have multiple receive and transmit queues. And typically, you can assign each queue interrupt request to a particular CPU core. So if you look in /proc/IRQ, you can see whereabouts each queue is going. Often, the kernel will dynamically move those around, but general advice is to disable the IRQ balance service and assign a particular queue to a particular CPU core. Certainly in the Intel cards that we use, the network card takes a hash of the source and destination IP address and the source and destination ports, and generates those, feeds them through another pseudo hash that the card initiates on boot, runs it through the whole cyclic system, and ultimately you end up with something that says, well, this packet's going to go to this port. What we found in the performance lab that I developed and presented on before, when using DNS-perf, is that you've got a single traffic generation machine and a single traffic receiving machine. So you've got a fixed source address, fixed destination address, you've got a fixed destination port. So the only variability in your source packets is the source port. And we found that DNS-perf is not amenable to using a large number of source ports. In fact, we're normally limited to about 24 source ports. And we're testing against a 12-core system. So ultimately, that doesn't provide sufficient entropy for the hashing algorithm to get packets flowing evenly across each of the 12 CPU cores on our inbound receiving system. So I normally find, looking at running on our perf lab with DNS-perf, that I'd find 1 or 2 CPU cores that may be maxed out. Some might be running at somewhere between 40 and 60%. Some CPU cores will be getting no traffic at all. Couple that with the way that Bind's older networking code works, where you're almost guaranteed a cache miss every time a packet comes in, because one thread might be handling packet receiving, and another thread is handling packet responses. And it's basically very, very far from optimal. hopefully at some point in the future, we'll get a talk from Andre or one of our colleagues about how we've refactored the network stack to get around that. But nonetheless, DNSPerf itself was found to be a limitation. I'll come back to that again shortly. You can further help the kernel, depending on whether you're talking normal user sockets or raw sockets. SO reuse port is highly recommended for any UDP traffic these days, because then you can have multiple user space sockets all on the same port, and the kernel then says, well, I'm going to wake that particular socket up, instead of having all the threads wake up and then all but one of them saying, actually, no, don't bother, because another one of the threads has been given the work. With even newer kernels, the SO incoming CPU option will not only wake up a single listener, but it will attempt to wake up a listener that is on the same CPU core as the CPU core that handled the packet in the first place. For raw packets, there are similar socket options available. As I said earlier, I am using raw sockets for this code, and I'm using the packet fan-out CPU mode. So again, the packets arrive as close as possible to the NIC, to the CPU core that handled the packet on the NIC. So relating to this, I've developed a couple of tools that are on our GitHub. I'll talk about those briefly. Because of the limitations with DNSPerf, I wrote a new internal packet generator. It's not intended to be quite as general purpose as the likes of Flamethrower, but the specific design goal was to get around this limitation and the lack of entropy on the flows. So we're currently using that on a 12-core system, defaulting to 4096 effective source ports per thread. So I'm using tens of thousands of source ports, and we get much, much more even flow of incoming traffic on the receiving system. Well, of course, for most people, if you're getting traffic on a recursive resolver or an authoritative server from the internet at large, you probably do have a very large amount of inbound source entropy. Something I was actually just discussing last week with Peter from PowerDNS, and this might be something I'll need to put in the documentation. If you've got DNS dist in front of a server pool, unless you deliberately specify the -C flag for clients as a very high value, you might well be inadvertently starving your backend server of flow hash entropy. So if you are using DNS dist in that sort of configuration, do look at your queues to see how that's working, because you may want to look at how you configure PowerDNS and improve that. DNSGen itself also loads DNSPerf files in the raw ASCII form, but I also have a tool as part of that that can pre-compiles the DNSPerf files into wire format, which loads very, very, very much faster. DNSPerf itself actually reads the file continuously as it's generating packets. My code instead loads the entire file at one hit, so it takes a few seconds to load up the 50-odd megabyte standard DNSPerf test file that they include. And there is also a raw socket-based echo server included in the suite, which on our hardware I've had working, from memory, about 7 million packets per second full duplex. So it's, DNSGen on the test system and echo server on the file system, 7 million packets of requests and responses at the same time. The other related tool, this is how you actually find out whether your queues are being exercised properly, is ETH-Q, which I coined as sort of top for NICs. On these multi-queue NICs, it is possible to look at how much traffic's going to each queue using the ETH tool command line utility, but you end up with a big, long ASCII output. They are represented in sort of SNMP style total counters. It's non-trivial to actually use that to see what the real-time rates are. So this tool is curses-based. It reads all of that data directly from the kernel every second, does all the work to translate the absolute counters into relative counters and per second counters. And hopefully you can see that on screen. You basically get transmit packets, receive packets, transmit bytes and RX bytes for each queue individually, and a total for the NIC as a whole. And the source code for that is also up on GitHub. One thing we do still need for that, is, depending on what network card you're using, is that ethtool does not have a standard representation for the queue names on the different NICs. There are a few generic names that are used by some network drivers, but many of the driver vendors or driver authors have used different ways of identifying the different queues. But it's fairly easy to adapt the source code once you actually know what those strings are. So if you try for queue and you find that it doesn't recognize your particular sort of NIC, please let me know, or even please send an pull request. And that's it. So any questions, please? No? Oh, it was Hazel.
Mostly, I just wanted to say thank you. This was a really good talk, and I will be checking out your ETHQ tool later.
Please.
Thank you.
Please
I'm sure we probably have something that does something like this, I hope, but it looks pretty neat, so I'm going to look at it. So, thank you.
Thank you.
Please identify yourselves when you come to the mic.
Yeah, sorry.
For the benefit of the recording, I'm Hazel Smith. Thanks.
I'm Jim Reid.
Hi, Jim.
Have been. Interesting talk, Ray, and I think it's fascinating to find out how you can sort of squeeze the last little bits of performance out of device, even relatively modest devices, by doing interesting things with the kernel. So I think explaining that is perhaps even more important than just playing around with this interesting little DNS server thing that you've got. I think that's very, very useful information for everybody. One question we'd have, though, is if I understand correctly, you're compiling the root zone file and feeding it into this box. What do you do when the root zone gets updated?
At the moment, I'm actually using dig compiled for the same architecture to basically do an AXFR. The daemon watches the file system for a new zone file being dropped in place, and then basically reloads it at that point.
I thought you said you didn't do AXFR.
No, I don't serve AXFR.
Okay.
Right, so yes, I can't serve AXFR, but I'm using an external application to receive AXFRs. There's no notify support. I mean, basically, yeah, we don't really want to be in the position where every single instance of this might suddenly be downloaded in the root zone the moment it's updated. So it currently just has a cron schedule twice a day, and with a random stagger so that they don't all fire up at the same time. Actually, sorry, no, I misspoke. Sorry, once an hour, it checks the SOA serial compared to against the one it currently has. And if it finds that the SOA serial has changed on the root zone, it then randomly backs off and schedules an XFR. And then the daemon itself just says, oh, there's a new zone file, I should reload. And the code says it's multi-threaded, it's lockless. So when the zone file is refreshed, it basically does a recompilation sort of outside in a separate thread, and then atomically just swaps that new zone file in place. So it's absolutely, it just doesn't skip a beat when a new zone file is there. It just keeps on going. If there are any outstanding queries that happen to be using the old zone data, those still get served, and as soon as the smart pointer references to those records are no longer being required, that zone just gets destructed, and it just keeps on running.
Good stuff. Nice work. Good work.
No, Joe's not correct. Yeah.
Ray, so I have a question. Anand Buddhadev, RIPE NCC. You mentioned that the daemon can listen on an IP. You mentioned that the daemon can listen on an IPv4 address
Yes.
and v6. Could it listen on 13 IPv4 addresses?
Are you talking about the real root server anycast addresses or any other 13 addresses?
Possibly, yeah.
Well, as I said in the talk, I mean, you should not, and well, you must not, but I can't stop people from doing it, use this software to emulate a real root server because it is not feature complete. If you have customers that want to or expect that you serve XFR, this does not do it. It doesn't serve the .ARPA zone. Currently, actually, the IPv6 support is linked local addresses only anyway. So it's specifically intended that you would configure a server to, a recursive server with a local area network address to which it's going to send the queries. And I don't particularly want to have this thing necessarily out there facing the public internet, not least because it is very fast when you run it on the right hardware, and it could be used as a very significant amplifier. There's no RRL in it, for example. The last thing I want is for somebody to get themselves a nice big fat serve with 10 or 100 gig of upstream bandwidth available and use this to fire out packets to the internet.
Thanks. I was asking merely out of curiosity.
Yeah.
Roy Arends from ICANN. Clearly, you have too much time on your hand.
I wish.
No. I know. I worked with Ray in the past, so I know how good he is in doing this and how quick he can do this. You started out by basically offering this as an alternative to RFC 7706. I understand that ISC bind now has the feature mirror zone.
It does, yes.
I personally, and this is a statement, not a question, I think the idea of mirror zone and using a bind configuration to host a copy of the root zone is preferred over specifically this. Compiling your own, putting it on a Raspberry Pi, throwing it in a network somewhere. But I think what you actually meant, to be honest, the idea of having a server in a network serving your entire network with root zone responses is preferred over having each individual resolver configured with the root
On
zone.
the larger scale, yes. I mean, I would love to be in a position where every ASN could have a local on-net root server to which they send all their traffic.
Yeah.
And it could be this, it could be something else. I mean, this, as I said, was primarily intended as a research project to learn about the networking stuff and how fast we can make the networking code work so that we can then feed that into what we do with bind. And looking at the network balancing and modern systems. You know, bind was architected 20 years ago. Well, multi-core was almost non-existent. And to be honest, in some respects hasn't changed that much in the way the networking code expects to talk to the hardware. So that was really the goal, but it happens to be aligned with some of F-Root's ambitions that actually, well, maybe we should have a root instance of some fashion, even if it's not a formal RSO-operated system, in every ASN.
I agree. Thank you, Ray. Great presentation. Thanks.
Olav Wermason, Cloudflare. Very good talk, Ray.
Thank you.
I was wondering if you were willing to do a little experiment to follow up on this, to deal with one of the holy cows of DNS. What would happen to your speed if you got rid of compression? Totally in the answers.
So compression is actually optional in the server. There's just a command line flag to turn it on or off.
Yep.
And the biggest limitation is actually the sizes of the responses. What I found was that if you looked in terms of packet rate rather than anything else, turning off compression basically dropped the packet rate because you could fit fewer packets on the NIC, basically on the downstream bandwidth.
Okay, so you're basically memory bandwidth limited on the hardware you're using.
On this particular hardware, I am NIC bandwidth limited. I wouldn't necessarily go far as to say memory bandwidth limited, but I'm certainly NIC bandwidth limited. I have a 10 gig E card, and with full-size answers with DNS-sec and so forth enabled, so typical average packet size of 700 or 800 bytes, more in some cases, depending on how many referrals there are. I'm hitting 2 million plus packets per second, but I'm saturating the 10 gig E pipe.
But there should only be 2 or 3 different answers that are going to be packet size limited. The DNS key.
It depends on the distribution of the eDNS options coming in as well. But I mean, for typical eDNS sizes, particularly when you do have servers that try to fall back to eDNS 512 or eDNS 1280 even, I found it did make a substantial difference between just how many packets were ending up saying, sorry, I can't fit that in, I'm going to truncate, instead of actually being able to send back an answer. I mean, it went from maybe 5% truncation to 25% truncation off the top of my head.
Don't listen to short requests. Just if they ask for 500 bytes, give them 1500. This is supposed to run on a local network.
Yeah.
There's no crapware in between, hopefully. So.
Yeah. But ultimately, they will get fewer packets per second out because, well, unless they're running a really, really fat pipe. And I haven't tried this on a 40 gig card yet. But yeah, at the moment, the card bandwidth is the limit.
Okay, thank you.
All right, thank you. Thank you.
Thank you very much, Ray. That was a very tantalizing presentation. Our third speaker for this afternoon is Petr Špaček from CZNIC, and he's here to talk about a tool called respdiff. Welcome, Petr.
Thank you for the introduction, Anand. I'm still Petr Špaček, hopefully still working for CZNIC. And this time I will talk about the interoperability testing tool we have. And I want to encourage you from the very beginning to think about what we can do better, because the purpose is not to show how good we are. The purpose is to find out what we can improve. So please think and don't be shy to say that we are doing it wrong. So, okay, motivation. In theory, interoperability is easy. You just read RFC, implement RFC, check that you've implemented RFC correctly, and that's it. But no, that's not how it works. In reality, people will complain that, bind can resolve this domain, but you can't, so you have to be wrong because bind is always right. Funnily enough, there is a beautiful RFC, 1925, my favorite one, and it has 12 networking truths, and the first one is it has to work. That's exactly what users expect, and yeah. Even more interestingly, there is one more point in this very same RFC, which says that even pigs can fly if you try hard enough. But the problem is that we shouldn't make pigs fly, and that applies to DNS protocol as well, because some of domains are just too broken, and we just should let them die. So in practice, interoperability is about finding the balance between the stuff which has to work because it's Google, Facebook, and YouTube, and the rest which, well, doesn't warrant workarounds. So finally, we are getting to the meat of the talk. We have a testing tool chain, which is like 10 or 15 different tools, which are very small, doing one very specific task, and we then chain them together to do interoperability testing. So we generate queries in wire format, then shoot the wire format on different implementations, gather responses, compare them, and then do some statistics on the resulting answers. So this is the basic schema. In practice, we have a tool which is called QPrep, which prepares the wire format query, and it is stored in the database on disk. Then we have different tool which is called Orchestrator. I'm sorry about the name, it's just we just didn't have enough imagination. And this tool takes the query from the database and shoots it to different endpoints. So it will, in this example, it sends the query to bind and not resolver. It's exactly same query bit for bit, but of course these two implementations are likely to give a little bit different answers. So the answers are then stored into the database again, and then the third tool in the pipeline, which is called messagediff, will again read the data from the database, do comparison on the wire formats and also on the parsed data structures, and evaluate based on criteria in the configuration file, and then spit out the result. So the tool chain has more tools, even more tools than I was able to fit on the slide. So in general, you generate queries, send queries, compare queries, and then do different statistics and generate reports about the differences you found, and draw latency histograms and stuff like that. This is an example of configuration file. So basically, there is an IP address, port, and protocol for every endpoint you want to test. And then there is a list of so-called criteria, which are basically the fields in the DNS answers which we want to match. So in this case, we are comparing opcode, rcode, flags, question, answer types. I will get to meaning of this in a minute. And then there is a configuration line called field weights. And the idea is that, okay, imagine that we have got two answers. Bind says no error, and there is an IP address in it. And the different implementation, let's say not resolver, will answer with serve fail. So obviously, these two answers don't match, and rcode is different. But in this case, when the rcode doesn't match, it doesn't make any sense to continue with comparison and compare flags, right? Because if one is no error and the other is serve fail, obviously flags are not meaningful. So basically the comparison stops and the first field where is a mismatch. So, okay. So now you have an idea what the tool does. So let's see how it works. When we were developing this testing toolchain, it was like, okay, let's see how it performs on like mature DNS software like years ago to see whether the idea is actually sound and whether it can give us reasonable results. It turns out that when we started to compare answers from bind and unbound, so not having not resolver, the new kid on the block anywhere else, we found out that there is way too many differences to actually make useful or allow us to make useful conclusions based on that. Because there is way too many load balancers on the internet which will send you different data, IP addresses and stuff like that in the answer. So if we are going to do comparison one by one, it's just not going to work. So we've tried something else. In the second attempt, we've started to ignore additional section and the authority section because in most answers like no error and so on, it's just too wild and not necessary technically. And also in the second attempt, we started to ignore the RData value. So we are looking only at sets of record types present in answer section, but we don't care about the actual IP addresses in there. So if one answer contains an IP address, IPv4 address, and the other answer also contains IPv4 address in form of a record, these are considered equal even though the actual IP addresses are different. This was much better, but still there was like 1% difference between bind and unbound at that point and that data set, of course, which is way too noisy for any useful testing, because if you have 1% difference all the time you run it, then what do? How do you analyze that? So the third attempt to actually do some useful interoperability testing was expanding the reference set. Because in the previous attempt, we basically said, okay, bind is the reference implementation, and we will compare unbound with bind. That didn't work because there was too many differences. In this third attempt, we said, okay, the bind and unbound at the same time are the reference. So imagine that we have one query and we send it 3 times. So once we send the query to the bind, second time we send it to unbound, and third time we send the very same query to the not resolver. Now we gather answers from all 3 and store them on disk. Then the comparison process starts, and we compare answer from bind and unbound, which are our reference, and compare them according to the criteria. If these 2 match, we continue and compare it with not resolver. If answer from in the other option, or the other option is that the answer from bind and unbound doesn't match for any reason. It might be hardcode mismatch or something else. In that case, our code decides, okay, this is too weird because even bind and unbound, which are around for like decade or more, can't agree on this. So probably the domain is hosted on something which is either broken in some way, or we are testing a feature of the protocol which is just not standardized enough to allow us any reasonable comparison. For example, if we were sending query of type any, that would be exactly the case, right? Because it very much depends on state of the cache, and you actually have no guarantee what you will get. So yeah. So now we are using bind and unbound as reference, throwing away everything which doesn't match for these two, and continue only with the rest. It turns out that that actually works. It cuts down the number of differences to a number which allows us to draw reasonable conclusions. Okay, so this is an example of the statistical output from the testing tool. So again, the query is sent 3 times, and the bold lines, the line which reads upstream unstable basically says that on this data set, bind and unbound didn't agree in 0.45% of cases, which means like we had data set around 500,000 queries, and 2,000 of them didn't match between bind and unbound. So we rule out these, and then what's left is disagreement between unbound and bind and not resolver. And that's interesting because these domains are, it seems that they are standard enough so 2 major implementations can agree how it should look like, but we can't, or we didn't agree. So now we can start looking into why the hell it didn't match. The report goes on, it has more detailed fields. So there is some statistics about particular type of mismatch, like for example, bind thinks that the answer should be no error, but the not resolver thinks it should be NX domain, for example, or something else. Or for example, the answer section in response from bind contains CNAME, but the not resolver responds with CNAME and quad A. And of course, the report continues on. So you can drill down and find out actual domain name and the query type, which causes this difference. That's nice, but sometimes when we were investigating these differences, it turned out that we are not able to reproduce the issue because sometimes it was just packet loss or some crazy other thing in the network. So we've written yet another tool, which is called diffrepro, like diff reproducer or something. And the idea is that you provide a script which is used to restart the resolver instance or flush cache or do whatever you need to do, and then run the script. This is how it looks like in practice. Basically, we ran the first test, and so, okay, here is like 300 differences. Then we run the reproducer, which basically starts all the resolvers again with empty cache and send the 300 queries which didn't match before, gather answers, compare them again, and it's checking whether the mismatch is there even on the second try or third try or how many you specify. And the differences which are not reproducible are just crossed out. So that's on the bottom right part of the slide. You can see that there is line not 100% reproducible and 100-something number. So using this technique, we ruled out basically half of the differences which were not reproducible at first try, and that allows us to concentrate on the problems which are actually reproducible. So it's much easier to just, have a look in logs and see, okay, this domain is weird in this way, or okay, this is a bug in implementation, we didn't expect that behavior, and so on. The problem is that 170-something differences is too much. We want to run tests as often as we can. In practice, we do that for every single merge request, which means like maybe 20 times a day, because it runs on every change in the merge request. So we have to automate the evaluation, right? I'm not going to use dig and go through a list of 170 domains after every commit. So now we are in the phase where we are trying to invent ways how to automatically classify the differences and find out what's actually an interoperability problem and what's just like minor difference, nobody cares. So there is a bunch of different approaches. We can look at the differences or the new stuff which we never saw before, or we can try to classify the domains based on the properties of the domain and not the result, and so on. So one of the possible approaches is basically have some reference data, like let's say that we have a stable version of not resolver. That's version 4.0. we run this test I just described, this comparison test, like 100 or 200 times and store results from these runs in one pile. Then I will do a code change, so I have a new version of the resolver, which is going to be 4.1, and I want to make sure that this new version is not more broken than the previous one, let's say. So I will run the testing pipeline again, and I have a new set of results. And one of the possibilities is to basically compare these two data sets, the reference results from the stable version with results from the new version, and see, okay, are there any new domains which were not in the report before, or how is the difference? There is a special tool called SumCMP for some reason, and that exactly prints the difference. Okay. We have also a visual way how to compare the results, because sometimes if you have like hundreds and hundreds results in text file, it's way too hard to actually make some sense out of it. So this is output of the tool. I will zoom in and explain what you see. This is the key to how you read it. On the very first column on the left, there is some gray background, and the gray background is visualization of the reference data set. So we ran the test 200 times with the same configuration, same data, same version of the software, and basically the gray background is histogram of results. So for that particular feature it is displaying, there was the lowest number of differences was 800, and the highest number was 2000 something. That's just the reference data. Second column from the left has basically one thing which is added, and that's blue line somewhere around 400. And the blue line indicates the value obtained in this test run. So now we can visually compare that, okay, in 200 runs on the stable version, we had this range of results, and the blue line visually indicates, okay, in this new version is standing in here, and it seems okay because it's like almost in the middle of all the reference data. So nothing suspicious there. The third column from the left has a red line, which is above, on top of the chart. And that's, again, the red line is the line with data from the last run on the new version. And now you can easily visually see that, okay, all the previous reference runs had a much smaller number of differences. So obviously we did something wrong because the value is like above the threshold. And the last chart on the right indicates that there is a green line on the bottom, and that's okay. So the previous reference runs on stable version had this number of differences, and now the green line indicates that we are way below all the number of previously seen differences. So we improved something, we fixed some bug. Now we agree more with bind and unbound, let's say. The post-processing is the hard part, right? Because visually I can see that I have some intelligence, hopefully. So for me it's not hard to classify, but for a computer it's much harder to classify, because sometimes when we were doing the reference runs on the stable version, as you can see on the very first column on the left, there is a gray blob. Let me see if, okay, there is a gray blob on the bottom. That's where the most of the reference runs ended up. And then we have one gray blob over here on top, because something was wrong with the infrastructure, or, you know, someone just pulled out the wrong cable in the rack or something. So the number of differences was too big. And the problem we have to solve, and we didn't yet, is how we can automatically classify, okay, this is like too weird, so it's a problem with testing infrastructure, or is it a problem with the code, or what? Yeah, of course, this is only one approach. There is like multiple different approaches we can take. For example, from the reference runs, we can have the list of domains which are always failing because it's like broken domain, and bind has and Unbound have some workaround which we are not willing to implement for one reason or another. And in that case, we can use this parameter without ref failing, and the final report will omit all the domains which are always present in the reference set, which means that they are always failing. So we can investigate only the rest, which is like new. And of course, again, I'm inviting you to come up with your own idea. The last we came up with in my team was to somehow classify the domain automatically based on the quality of the domain. The idea was basically run DNS-Wiz on set of domains which ended up in the different set and categorize them to the OK domains, domains which are flagged by DNS-Wiz with some warning message, and the error ones. And obviously, if there is a problem or difference in resolving on a domain which seems to be perfectly okay, perfectly according to standards and best practices, that's more serious than if we don't agree on answer from a domain which is like broken even according DNS-Wiz. Here are some links. Slides are available, so I will, you can try it yourself. Code is open source, is GPLv free. Feel free to take it, play with it, report issues. And now it's your time. Please give us advice what we can improve.
Matthijs making ISC. Before I start in improvements,
sorry, I can't hear you. Can you be closer?
Before I start talking about improvements, I'd rather first do some questions. I like this. First question. Resolvers have many configuration options. Are these configuration of the resolvers out of the box, or have you tried to match like features and?
That's configuration of the resolvers is out of scope for this tool. So you provide configuration file whichever you want.
Okay.
You have to start the resolver. This tool only sends the queries and gathers answers. So, it doesn't do any magic with configuration.
But you run the test with special configuration then?
Well, yeah. I mean, in practical use, you have to decide what you want to test, right? So you configure the resolver according your needs. I mean, it might be even eDNS buffer size, which has to be the same, right? Or stuff like that.
Right, so the results that you present, the percentages are based on sort of similar configurations, like you...
Yeah, these were like actual numbers from our test pipeline.
Okay. The second question I have is that you said you would do bind and then unbound, check it, and if they are agreed, then check not. Have you actually tried doing not and bind, for example, and then unbound, or a different configuration?
No, I didn't, yeah.
Okay. It would be interesting to see there if there's major disagreement, because maybe not is the more newer resolver, and yeah, so if there's difference in numbers there.
Well, there will be some differences, but the thing is that even bind and unbound can't agree on a lot of stuff. So I wasn't even trying, the new implementation, because it will be even like bigger pile of thing to go through.
Cool. And I think the last question I have is the few differences that you have. Can you tell us something about what the differences are? Were there implementation errors or?
I mean, it's magic. If we knew, we would fix them.
Okay, so there's nothing that you found like, okay, fix this in the code, or?
It's not one single thing. That's the problem. Because that's the reason why we need some way how to classify them, because we went through the list of differences like a couple of times manually, but it takes a lot of time, and in the end we often found out that, okay, this is just weird authority server, which, returns serve fail like 4 times in a row, and then it works for a couple of queries, so it just, doesn't match.
Okay. Well, thank you for the presentation. It was great.
Matt Poundset. So if I understand correctly, this is intended to test the protocol implementation for right?
Yes, exactly.
So on the topic of suggestions, something like this could also be very useful for testing provisioning. So for testing the content of the data as well as the protocol implication. I was working on a project a few years ago to re-implement provisioning for a registrar. We were switching DNS implementations and completely redoing provisioning, and we ended up having to write a tool like this in order to test responses from current production and the new system. And one of the things that we found was really useful is we essentially created a bit of a configuration language to describe expected changes. We've fixed for example, one of the things that we fixed was to get rid of CNAME at Apex in the provisioning. So we expect to see that change from one to the other. So we want to classify that as it's different, but we expect it. And so something like that would probably be useful too.
Okay, thanks for the suggestion.
All Guims on Cloudflare, very nice. We have a very similar tool internally, and we use it slightly differently. We basically use it to compare the prior version of a software or configuration to the new one, so we can see what is changing, and it's very useful for that. As for your suggestions for future work on your part, it would be wonderful if you could get somebody to put this tool up and ask a bunch of resolvers the same question, because we always get this issue that people say, but this resolver resolves it.
Yeah.
And well, it may depend on your point where you are, or it's a timing issue. So having something that would test from multiple places on the internet and compare the results in real time when you press a button, that would be useful. And I think this would be very useful to augment with DNS Viz.
Yeah, that's right.
Thanks.
I have to adjust the mic after Oliver's been there. Jim Reed, great work, nice tools. I'd like to see more of this kind of thing. This is probably a question or something for further work, Peter. What about some of the funkier things you might see in the resolver scene? I'm thinking particular things like TSEG records or EDNS goop around things like ECS client subnet or cookies. Is that something you've considered for further work? Or?
Well, the thing is that the tool is processing basically blobs. So you can even put invalid stuff in there, and it will just shoot at the server, get the answers, and then do whatever with it. I mean, right, it's super easy to extend. So
okay,
it's Python 3, and it should be like written. It's fresh code, so it shouldn't be that horrible.
Yeah, Včelák, NS1. Thank you. Looks really useful. I'm interested in the stuff that you discard, because there is disagreement between the two resolvers that you use in the comparison. Have you looked into the data at least a little? Is there some common denominator? Is it a list of domains or a list of IP addresses, list of providers?
From what I saw, it's like completely all over the place, but it's like little things. I mean, the data set we are using is like 500,000 queries, and the numbers you saw on the slides, which are in order of hundreds, are real, which means that it's like little things over here and there, and I wasn't able to find like common pattern to them. Otherwise, we would have fixed them already.
Okay, because I think if there are these small things, it could be something actually very useful. But yeah, thank you. Nice work.
Thanks. Sorry, I overlooked you.
Rubens Q-Link.pr. Have you thought in combining that with trace debugging, so you know that differences come out of a single subroutine or different subroutines? Because that would allow you to minimize that and say, hey, this only happens when code uses that method from that object, or this happens all over the place. So this is
okay. I'll think about it. That's interesting. Yeah. In reality, we do all the queries in parallel, or not all of them, but we have like 300,000 threads doing 300 threads doing the queries. Otherwise, it would take too long. But 500,000 queries is done in like 2 minutes or 3 minutes or something, and we run that stuff in 8 different configurations all the time. So that's why often Jeff Houston complains that we replay his queries. And he sees queries which he's not supposed to see ever again because it was unique query, but we are replaying pcaps and then comparing stuff. So, okay, thank you for the suggestion. I will think about it.
And just one small addition. You only mentioned comparing to bind and unbound, but you probably have access to some network operator that uses a commercial DNS precursor, such as Akamai Vantio. So you could compare to that as well, because if you are a client, you just relay queries to them and see how they respond to you. So
yeah, theoretically, yes. Thank you.
Thank you very much, Petr. So this brings us to the end of our session now, and there is a coffee break. The session after this will resume at 4 p.m., and that's when we have the lightning talks, followed by reports from DNS-OARC and administration. Before you all disappear for the coffee break, I'd like to remind you again, please fill out the surveys. They help the OARC organization and PC to keep producing a good program for upcoming meetings. And it's also good feedback for the speakers. You will find links to the surveys on the rolling slides on the screen. And if you can't find them on the screen, you can also go to the OARC 30 website, and the links to the survey are also available there. So please do take a few minutes and fill out the surveys. Thanks, everyone. Enjoy coffee.